Hello. While our pot still technology has been around for millennia, the drive for efficiency and accuracy with regard to fraction delineation has led to technological advances. About 200 years ago, methods and tools were developed to greatly enhance distillation science and dramatically increase efficiency and purity of our distillates. We're talking, of course, about the column still. Let's dive in. Welcome to this advanced lecture on column still technology. For centuries, batch distillation using copper pot stills defined whiskey production. But the limitations of pot stills, namely their inability to produce highly rectified spirits and their reliance on batch processing, spurred innovation. The modern column still, often referred to as a patent still or coffee still, revolutionized the spirits industry in the early 19th century. This technology allows distillers to overcome these traditional challenges, enabling the creation of highly rectified or even neutral spirit, while also facilitating high-volume, continuous production. But while column stills are critical for producing neutral grain spirits and base whiskeys like Scotch grain whiskey or Canadian-based whiskeys, they are also adaptable, serving in less rectified capacities for spirits such as bourbon and Armagnac, where flavor retention is key. Our focus today is on the complex design, the physics of reflux, and sophisticated operating procedures that manage flavor compounds or congeners spread across the height of these towering fractionating columns. Nearly all column stills are heated using steam, with direct heating being rare save for specific traditions like in Armagnac, where it's a legal requirement. Steam provides precise, controllable heat, vital for successful column operations. Distillers utilize several key indirect steam heating methods. Our reboilers are external heat exchangers constantly pumping the liquid being distilled out of the still, where they pass it over hot surfaces and recirculate it back. This ensures a large heating surface area and minimizes the risk of scorching any solid particles by keeping the liquid in constant rapid motion. Now, we can use steam jackets. These are mounted externally on the still. Jackets can apply very even heat over a large surface area, leading to high efficiency and a pretty low scorching risk. But then we can also use coils, and these are submerged pipes carrying steam like we see in pots, though these are less common in new designs due to the inherent scorching risk. For operations involving high solids content or those seeking minimal new flavor compounds, direct steam injection is sometimes used, particularly in very large operations. And while this method efficiently extracts volatile fractions, it's introducing water into the system, which must be removed later. Crucially, though, it significantly reduces the occurrence of Maillard reactions, those browning reactions that add flavor, allowing distillers to produce spirits with light or neutral aromatic intensity. The primary function of a column still is achieved through its internal structure, designed specifically to control reflux. This control is managed either by rectification plates, this is the most common method, or by what's called a packed column. Rectification plates force rising vapor to bubble through a layer of descending liquid, ensuring some interaction. Conversely, packed columns use material like metal or glass rings to create an enormous surface area, achieving separation through less ordered yet numerous little condensation pockets. We do see these used commonly in Asian spirit traditions like in Baijiu. The core principle of continuous distillation is the systematic separation of components based on their volatility. As a preheated fermented alcoholic liquid, known as the wash or beer, enters the column, the still divides into two key operational zones. The stripping section, which is the bottom half. This is located below the feed entry point. This is the hotter section responsible for stripping the ethanol from the wash. Then we have the rectifying section. This is the top half, located above the feed entry point. This is the cooler section where vapor enrichment occurs. Within the rectifying section, the mechanism of rectification really gets started. Vapors enriched in the more volatile component, ethanol, rise up the column. When these vapors encounter the cooler descending liquid known as reflux, they condense and reboil. At every plate, the vapor rising up gains a higher concentration of ethanol, while the liquid flowing down gains a higher concentration of water. For distillation engineers, the relationship between liquid and vapor composition is mathematically modeled using the vapor-liquid equilibrium curve to determine the number of theoretical plates they require. The operational efficiency of the column is defined by what's called the reflux ratio, which dictates the amount of liquid returned down the column. A still designed to produce highly rectified spirit, reaching 95% or 96% ABV, requires a lot of these plates, often 40 or more, to systematically drive the ethanol to the top, leaving near pure water waste at the bottom. Emphasis on nearly. The primary advantage of the column still is its ability to reach and maintain dynamic equilibrium. This is the stable state where the concentration of fractions on every plate remains constant, allowing the distiller to collect various outputs from different points simultaneously. Getting to this state requires very careful startup procedures. Hot water and steam are introduced to warm the column and initiate the molecular movement of fractions. Initially, the ethanol concentration in the distillate is reduced, and this liquid, known as cold faints, is collected separately and fed back into the process once the system stabilizes. Once dynamic equilibrium is established, continuous operation requires strict control over two parameters. One being our flow rates. The volume of fermented liquid entering the still must precisely match the volume of liquid and vapor exiting the still. If the spirit takeoff is reduced, ethanol losses can occur in the spent wash. Temperature. The temperature difference between the top and bottom of the column must remain constant. Any temperature fluctuation on a plate will cause less volatile fractions to either rise or fall in unpredictable amounts. By maintaining this equilibrium, column stills deliver a spirit of remarkably consistent quality and allow for the continuous linkage between the batch fermentation process and the continuous distillation process. Now, column still designs can still vary significantly based on their rectification goals. The coffee still, also called the traditional double column, was patented by Aeneas Coffey in 1830. This utilizes a double column setup, a stripping column or the analyzer, and a rectifying column. A key feature is the integration of the preheating system. The cold wash flows through a pipe coil inside the rectifying column. This heats the wash before it enters the stripping column, while simultaneously cooling the vapor in the rectifier, promoting enhanced reflux. Heat efficiency is further improved by often including a thermal compressor to recover heat from the spent wash. Then we have our Irish grain 3-column system. This is a more advanced implementation as seen in Irish grain whiskey production, such as the former Middleton system, which employs a 3-column unit consisting of a beer column and a 2-column extractive distillation unit. The purpose of this design is highly specialized congener separation. A dilution water stream is added at the top of the extractive distillation column. This changes the volatility of higher alcohols, aldehydes, and esters, causing them to concentrate higher up the column. The congener-rich vapor at the top is condensed, and the resultant fusel oils are separated via a decanter. Unlike batch stills, where fractions are spread over time, in a continuous column, congeners are distributed and concentrated across the height of the still. This enables distillers to continuously draw off specific fractions. Our highly volatile compounds, or heads, our group 1 fractions, such as methanol, concentrate at the very top of that rectifying column. To avoid collecting these undesirable compounds, the desirable heart, highly rectified or even neutral spirit, is drawn off several plates below the top. Extremely pure neutral spirit production may utilize a separate heads distillation column, similar to the de-methylizing column, to achieve even greater control over these volatile compounds, but we'll talk more on that in a minute. As far as our group 3s, these less volatile compounds, categorized as tails or fusel oils, these are isoamyl alcohol. These concentrate lower down the rectification column, where the ethanol concentration gets lower. If these are not removed, these compounds can reach their solubility limit, leading to undesirable off notes and even cause foaming that significantly disrupts still function. These are typically extracted via a side stream near the base of the rectifier where their concentration peaks. To avoid loss of product, the fusel oil stream, which still contains quite a bit of ethanol and flavor congeners, is often passed into a small rectification column. This little dedicated column, often packed with copper, stainless steel, or ceramic rings, uses steam to further fractionate those components, allowing the recovered ethanol flavor stream to be returned to the still, and the almost pure fusel oil stream to be completely removed from the system. Now, you think we'd be good to go with these mini column stills and a near pure spirit, but we're actually not there yet. Our olfactories are pretty amazing, and for instance, can still pick up hydrogen sulfide at about 0.0005 parts per million. For spirits requiring even greater purity, such as vodka or high purity grain neutral spirits, multi-column systems are employed. These systems utilize specialized columns to target specific congeners. So while we have our myriad of compounds vaporizing and concentrating at different temperatures, like here's ethanol in a typical column and some of our other fractions. So it's still not pure fraction collection, although potentially much more defined than what we can get out of multiple pot distillations. So imagine we still have some amount of fusel alcohols that we want out of our spirit. A common redistillation process called hydroselection can drastically reduce those few remaining fusel oils. By diluting a highly rectified spirit down to approximately 20% ABV, those fusel oils suddenly become much more volatile, causing them to rise to the top of the hydroselection column for removal. The diluted spirit is then transferred to another rectification column to concentrate the ethanol again. I know that doesn't make sense, does it? But these fusel oils and some other heavier alcohols have a somewhat confusing behavior. Isoamyl alcohol, for instance, which is less volatile than ethanol overall, yet it behaves as more volatile than ethanol in high water, low ethanol concentrations. How does that happen? So it's less volatile. Back in our rectification section of the column, where ethanol concentrations are high, isoamyl alcohol behaves according to its high boiling point. It is the least volatile major component compared to ethanol and water. So it moves down the column and concentrates in the liquid phase near the base of the rectifier, or where we pull it out in that side stream, lower down the column. This is usually at an ethanol concentration of about 40 to 47%. That's simple enough, right? But the volatility reverses in low ethanol, high water environments. The mixture of ethanol, water, and fusel oil is not a simple, consistent chemical solution. The components interact, especially in the presence of high concentrations of water. Just to get geeky here, isoamyl alcohol forms a minimum boiling heterogeneous azeotrope with water. If you remember, an azeotrope is that's a mixture that boils at a constant temperature and has a vapor composition equal to its liquid composition, effectively reversing the expected volatility order. Isoamyl alcohol and water form an azeotrope that boils at around 95.2 degrees. If we dilute our highly rectified spirit and send steam injection in at the bottom and even hot water at the top, the amount of water is high enough to drive the formation of this water isoamyl alcohol azeotrope. The volatility of this azeotrope system causes the isoamyl alcohol to be carried up with the vapor more readily than expected, even becoming more volatile than ethanol, especially when our ethanol concentrations are below 40% ABV. This helps the fusel oils, like isoamyl alcohol, to actually move up the column to be removed. Then we redistill our more low ABV liquid to pull out the ethanol. But now we've reduced the group 3, so it's an even more pure after this hydroselection process. In essence, the distillation process is governed by the relative volatilities, which are not constant and dramatically change depending on the local concentrations of ethanol and water within the column. And just while we're talking about these heavier fusel or group 3 alcohols, you have probably heard them called fusel oils. How does that come about? Well, common in batch distillation, or if we've pulled those group 3s off at that 40% ABV level, if we let them cool down, they lose their affinity for water and act like oil, as in oil and water don't mix. In our bourbon stills, we often run the beer still through the heater where it cools and drops some group 3s. And we can have a collection tank before the doubler, or in between the wash still and the spirit still where we got to that 30% ABV. We can let that cool down and some of the fusel alcohols or fusel oils will separate from the liquid and float to the top. We can pull from the bottom of this container, or again, sometimes it's a little packed column of its own, and then either feed that higher ABV back into our column or use that cleaner low wines to go into our spirit still with lower levels of group 3s prior to a second distillation. If the fusel oils are not efficiently removed through a dedicated side stream, they build up until they reach their solubility limit. And this results in that foaming in that area of the still, which significantly reduces the ability of the still to function and imparts an off note to the spirit. Another danger is fouling of these stills during distillation, especially when using unfiltered worts. This process is exacerbated by materials like the high glucan and husk levels found in barley, which can cause significant fouling and crust formation that just completely destroys the process's efficiency. Unmalted barley and wheat particulates are also concerns here. Additionally, if your inputs vary, you're gonna mess with that dynamic equilibrium. So even with the increased efficiency and huge amount of product a continuous distillation system can provide, it's not a simple process to execute. And we were only talking about fusel oils and group 3s. Let's look at group 1s now, and specifically methanol. You would think there can't be much methanol hanging around if we cut them out judiciously. But we humans can also detect methanol in water at around 50 parts per billion. That's billion with a B. If we are dealing with very light character, highly rectified, which means high water spirits at bottling, this can be a problem. Also, they can't hide in a pile of other congeners. Additionally, in the EU, the tolerance for poisonous methanol is very low. And if our raw materials were potatoes or some of our fruit, we will have too much methanol even in our neutral spirit. So we can take our highly rectified spirit and run it through a de-methylizing column. As opposed to our fusel oils, methanol is easier to separate from ethanol when the alcohol by volume is very high. To maintain this crucial high ABV condition, the column must be designed and operated carefully. Distillers will gently heat the column using a reboiler rather than direct steam injection, as steam injection would introduce water and dilute the spirit, ruining the separation efficiency. Within this de-methylizing column, the volatility difference between methanol and ethanol, enhanced by the high spirit strength, causes the methanol to become concentrated at the top of the de-methylizing column, where we can pull it off, allowing the spirit to achieve extremely high purity. We can then pull the purified, even more neutral spirit from the base of this demethylizing column. Now, we've discussed copper in the distillation theory and pot still lectures, and as you might imagine, it's important in column still construction. While many modern plates are made of stainless steel, copper is still essential for removing highly volatile, undesirable sulfur compounds like dimethyl sulfide and dimethyl trisulfide. So we do almost always incorporate at least copper plates in the rectification section, or by providing sacrificial copper services in condensers or tanks. Specifically, sacrificial copper is used in stainless steel American bourbon beer stills to absorb methyl carbamate, reducing the formation of the carcinogen ethyl carbamate. Those fast-running columns in bourbon and that variety in grain bills means it's more likely to occur than in slower, often gentler Scottish-style double pot distillations. So those gleaming, easy to clean, and long-living stainless steel immense columns still will want a way to get copper involved, requiring regular cleaning with both alkaline and acidic cleaners. Scale significantly reduces heat transfer and increases resistance to fluid flow. Direct injection of steam, rather than using heat exchangers, is often employed to prevent fouling caused by the burning effect on these reboiler tubes. Now we're going to mention hybrid stills briefly, and they probably belong in the pot stills lecture, but they are part pot, they're batch processed, but they have a column on top. But these are a recent development that offer flexibility, particularly to micro distillers. These are the hybrid stills. This unit incorporates a traditional pot, a column, typically with rectification plates and a deflegmator, and a condenser. Now, as I said, they don't really belong in a column still lecture or at least continuous column lecture, but they do use column technology, so we'll quickly discuss them here. While column looking, these hybrid stills operate in batches, allowing distillers to bypass the column entirely if they want for traditional pot distillation, or to direct the vapors through the column for enhanced rectification and the ability to really fine-tune those cuts. We can activate as many of the plates as we want, depending on our desired result. When utilizing these hybrids, the process involves heating the pot and reaching dynamic equilibrium in the column, and then using the deflegged to control the precise degree of reflux by controlling the temperature at the still head. We can get all or most of the head sitting in the column below the defleg. This level of control allows the initial spirit collected to be at a significantly higher strength, often above 90% ABV, even with only, say, 10 to 12 plates, compared to a traditional pot still. This high purity potential makes the hybrid still attractive for creating clean, defined spirits, or dialing in the exact fraction composition for collecting other congeners in more characterful spirits. So from the early coffee stills developed for Irish grain whiskey to the complex multi-column systems used for ultra-pure neutral spirits, the column still remains the epitome of distillation efficiency. It allows for, but does not guarantee, high throughput, consistent quality through that dynamic equilibrium, and precise congener management across both the light and heavy flavor spectrums. Understanding how distillers manipulate heat, reflux, and product cut or takeoff points is fundamental to appreciating the technology that underpins the vast majority of the world's commercial spirits. See you next time.